Okay, I think we can continue with the final session of the workshop. I will briefly present the overview of the two shared tasks that we organized, and then we will have two presentations from the winners of the two shared tasks. And at the end, there will be a brief closing remark to summarize this workshop. So thank you so much for your attention, and I think we can continue with the presentation. Just share my screen. Okay, thank you everyone. So for this presentation, I will talk about the acronym identification and disambiguation shared task that we organize in the scientific document understanding. The organizer of these two tasks are the same organizer as the workshop. So the first task, acronym identification, aims to find all mentions of the acronyms and long forms in a piece of text. For instance, in the given example, we have two acronyms, KPI and E2E. And also we have a long form, key performance indicator, which is the expanded form for the acronym KPI. And we expect that the systems to find all mentions of the acronyms and the long forms in the given sentences. For the second task, acronym disambiguation, the goal is to correct and to choose the correct meaning for an ambiguous acronym in a sentence. And ambiguous acronyms means that an acronym that could be expanded to different phrases. And it depends on the context. For instance, in the given example, we have the acronym CNN, which could be expanded to convolutional neural network or cable news network. And the correct expansion depends on the context. For instance, the words vectors and representations are helpful for us to know that the correct expansion is convolutional neural network. For both of these tasks, we have a bunch of previous works, and for the specifically for acronym identification, the rule-based models are the most common approach to use. For instance, uh, the previous work have used some predefined patterns, such as the phrase that precedes an acronym, which is inside a pair of parentheses, is actually the expanded form of that acronym. So, for instance, in the given example, convolutional neural network is the expanded form of the CNN. Or they may use other sophisticated features and use them in a statistical model, such as support vector machine or conditional random fields. We also have some previous work for acronym disambiguation. In addition to the feature-based models, recently deep learning has been widely used for this task. And we can categorize these works into language-based models and deep architecture, the models that use deep architectures. The language-based models try to embed the different meanings of an acronym in an embedding table that will be fine-tuned on the training data. And then based on the similarity of the embedding of each meaning and the context, we can choose the correct meaning. And the deep architectures formulate these tasks as a classifications, and they may use, for instance, LSTM, convolutional neural network, or even graph convolution network to encode the sentence and the context, and then they perform the final classification. But the limitation of these works is that, firstly, most of these works are evaluated in the biomedical domain. And we know that in other domains, such as scientific domain, we have a lot of acronyms. So it is important to evaluate these models in these other domains too. And we also know that the existing datasets for acronym identification and acronym disambiguation are very small, and they may be even unsupervised, which is not perfect for deep learning models that are data hungry and we require a lot of training data to have good performance. So we try to address these limitations. For the acronym identification task, we create the largest available manually annotated dataset for acronym identification. These dataset is created from a corpus of more than 6,000 scientific papers obtained from the archive, and we select more than 17,000 sentences that are likely to have an acronym and also the expanded form of it. Then we annotate this dataset using the mTorch. Each sentence is annotated by three workers, and they annotate the sentence for the mentions of the acronym, the long form, and also the mapping between them. We call this dataset SciAI, and in comparison to the other existing dataset, this one has the is the largest one, and also it is publicly available. And using this dataset, we create another dataset for acronym disambiguation. Firstly, we need to have a dictionary for the acronyms to create this dataset. So using the mapping that we have between the acronyms and their long forms from the SciAI dataset, we create a dictionary of more than 700 ambiguous acronyms, which means that acronyms that have more than one meanings. On average, we have 3.1 meanings per each acronym. And then we use the assumption of 1 sense per discourse to create the dataset, which means that for every document that contains ambiguous acronym, and also it has the expanded form of the acronym, we will take all sentences that mention that acronym in that document and annotate that sentence with the corresponding expanded form. And using this process, we can create a dataset with more than 62,000 sentences. And compared to the other existing dataset for the scientific domain for this task, acronym disambiguation, this dataset, which we call it SciAD, has more training samples. So it could be a better benchmark for evaluating the existing models. Using these two datasets, we organized two shared tasks for acronym identification and disambiguation. The training phase started on September 1st and ran through November 20th. And the evaluation started on November 20th and it ended at December 4th. And for the acronym identification, we had 54 teams registered and 18 of them participated in the evaluation phase. They made more than 200 submissions in total, and they have used rule-based methods, some statistical models, and the majority of them are using transformer-based models. Also, for the acronym disambiguation, 44 teams registered and 12 of them participated in the evaluation phase. They made 187 submissions in total in the evaluation phase, and again, feature-based models and also the neural networks have been used. But the majority of the works are still using the transformer-based language models such as BERT and Roberta. And here are the results for these two shared tasks. For the acronym identification, we provided a rule-based baseline, and the participating systems made a significant improvement over this baseline. However, we still have a gap between the human performance and the best performing model. So there is room for improvement on these tasks. And also for acronym disambiguation, we provided a baseline. We choose the acronym with the highest frequency in the training data as the prediction for the disambiguation. And again, the participated systems significantly improved the performance compared to this baseline, but we still have a gap between the best performing model and the human performance. So we still more research is also needed for acronym disambiguation. And in future, we expect that comprehensive evaluation benchmark to evaluate the models not only on the scientific domain, but on financial or social media domain is also needed. We expect to have a more comprehensive dictionary of ambiguous acronyms with more meanings per each acronym, and also to cover more ambiguous acronyms. We also expect to see some methods that could use the power of the generative language models for either acronym identification or disambiguation. And finally, we expect that some research to show that how acronym disambiguation could be used in downstream tasks, for instance, for question answering or information extractions. It could be another direction to see in the future. So thank you so much for your attention. And if you have any questions, feel free to ask me. And otherwise, we can move on to the first presentations of the winner of the acronym identification task. Okay, the uh, presenters for this session unfortunately are not able to present their work live, so I will just play back their pre-recorded presentations. And if you have any questions, you can directly reach out to the others. And also, we have a poster session. So if you want to get familiar with the other systems, I encourage you to join us in this poster session, which will be held in virtual chair in room E from 4:30 to 5:30.
Hi everyone, good afternoon. I'm Zhu Danqing from Alibaba Group. Today I'm going to introduce our work on adversary training bot for acronym identification, which is the winning solution for shared task 1 of SDU. This is the outline of the presentation, which mainly includes 4 parts. Our task is acronym identification. It aims to identify acronyms and their meanings from the documents. For example, an input sample is existing method for learning with noise labels, LNL, primarily take a loss correction approach. We hope that the model will identify that the acronym is LNL and the corresponding phrase is learning with noise labels. This task is modeled as a sentence-level sequence labeling problem. Traditional work uses statistical approach such as HM and CRF with handcrafted features and task-specific results. With advance in deep learning, many existing state-of-the-art neural sequence labeling models utilize word-level STM structures to represent global sequence information, and a safe layer to capture dependence between neighboring labels. Our work is based on BERT, so briefly review how BERT solves the sequence labeling problem. BERT is a multi-layer bidirectional transformer encoder trained with a mask language modeling objective and the next sentence prediction task, which requires task-specific fine-tuning. BERT trains an encoder that generates a contextualized vector representation for each token as a hidden state. The hidden state is then fed into a fully connection layer with a softmax unit to obtain the predicted probability distribution for each token. The model is trained with the cross-entropy loss function. There are two main challenges in acronym identification. First, the origin BERT paper mentioned. For BERT large, we found that fine-tuning was sometimes unstable on small datasets. In the past 2 years, many studies have shown that the BERT large model does not perform well on small datasets. Second, our task is a complex sequence labeling problem with non-contiguous entities. For example, convolutional and/or recurrent neural nets are long forms, and there are 3 corresponding short forms, namely CNS, RNS, CRNS. Adversary training is an important way to enhance the robustness of models by adversary samples. An adversary sample is an instance with small, intentional feature perturbation that induce the model to make a misclassification. As shown in the figure 1, the orange model classifies the picture as a panda with a confidence of 57.7%. But after adding a small perturbation, the orange model classifies the picture as a gibbon with a confidence of 1990.3%. In the procedure of adversary training, the input samples will firstly be mixed with some small perturbation to generate adversary samples. The model is trained with both the orange input sample and the generated adversary samples to enhance its robustness and generalization. Madry abstracted the general form of adversary training as the max-mu and min-mu formula, where x represents the embedding vector of the input token. R underscore idv is the perturbation applies to the input, and IR is some loss function like cross entropy. First, the internal maximization problem is to find the best perturbation at the given data point x in the perturbation space to generate adversary samples that achieve high loss. This can be seen as an attack on a given neural network. Second, the goal of the external minimization problem is to find the model parameter theta to minimize the adversary loss given by the internal attack problem. How to apply spore perturbation to the input sample to generate adversary samples? There are many related studies on adversary training such as the fast gradient descent method, fast gradient method, projected gradient descent. Since those can basically be regarded as a series of methods, I will briefly introduce the FGM algorithm with this training time. The main idea is to add a perturbation to the input that can increase the loss. It happens to be the direction in which the gradient of the loss function rises. Specifically, the adversary perturbation is defined as follows, where g is the gradient of the loss with respect to x. The L2 normal is used to constrain g in equation 3, and the epsilon is a hyperparameter and defaults to 1. In the acronym identification task, the perturbation will be added to the embedding of the input token. This is the overall architecture of the proposed 80-BERT approach. The whole training process is divided into two steps. In the first step, the black line represents forward propagation, and the red solid line represents backward propagation. The purpose is to obtain the perturbation gradient, so the parameter will not be updated for the first step. The second step is to use the gradient obtained from the backpropagation in the first step to generate adversary samples. The red dashed line indicates the backward propagation that will update the parameter. We evaluate all models based on the dataset provided by SDU. It contains a training set of 14,000 samples. All models are implemented based on the open source transformers library of Hugging Face. In addition, we use two V100 GPU to complete these experiments. For the above models, we don't modify the orange network structure and the parameters. The only special thing is to modify the Albert nanounit. Regarding the evaluation metrics, the results are evaluated based on their macro-averaged precision, recall, and F1 score on the development set, computed for correct predictions of short-form and long-form boundaries in the sentence. Among the 6 different BERT-based models, the ACI BERT model has the same architecture and training strategy with BERT-based. However, the ACI BERT, whose corpus is more relevant to our task, outperforms BERT-based with 1% increases macro F1 score. Meanwhile, taking advantage of large training corpus and a more effective training strategy, the performance of other BERT-based models like RO-BERT and Electra get further improvement. With the fast gradient method adversary training strategy, we can clearly observe that the 80-BERT based models outperforms those without adversary training by a large margin. From the comprehension of ensemble average strategies, we can find that the 80-bird ensemble model is perform best is more advanced than the best method, the rule-based method, and the LS team CRF model, with 8.6% and 7.5% increases macro F1 score, respectively. However, the best performance is still less effective than human performance, thereby providing many research opportunities for this task. We further analyze the prediction results of BERT and AT-BERT. This sample is very confusing because the recurrent neural nets can be considered as the long form of RNNs, and the general BERT model might be easily affected by the token and all, and ignores the previous token convolutional. The experimental results prove that our proposed AT-BERT does have better robustness and generalization. We propose a novel framework for acronym identification, including a pre-trained BERT for the semantic representation, an adversary training strategy to make the model more robust and generalized, as well as a multi-BERT ensemble mechanism to achieve superior performance. In the future, we will optimize our model from two perspectives. One is to explore more adversary training strategies such as PGD and FreeRB for BERT model. The other is to try different loss functions such as dice loss and fork loss to elevate the phenomena of class imbalance.
Okay, thank you for your attention. And again, if you have any questions regarding this work, please directly reach out to the authors. And if there's no questions, we can move on to the next presentation, which will be the winner of the acronym disambiguation task. Um, Again, this is another pre-recorded presentation, and I encourage you to reach out to the authors if you have any questions about that.
Hi everyone, we are Deep Blue Eye team from Deep Blue Technology in Shanghai, China. Next, we are going to introduce you about our work for SDU Share Task 2, which is about acronym disambiguation. An acronym is a word created from the initial components of a phrase or name. For example, SVM can stand for Support Vector Machine or State Vector Machine. Given a sentence with an acronym and several possible long forms of this acronym disambiguation task is to determine which long form is the correct one for the particular context. As shown in the screen, Support Vector Machine is the correct meaning here for SVM. In this task, we use the AD dataset called SCI-AD, released by the organizer of SDU workshop to train the model. This dataset is collected from thousands of English papers from arXiv. It contains 62,441 samples and have 732 acronyms. Figure here shows the distribution of number of long forms per acronym. We designed our binary classification model for acronym disambiguation based on BERT. Since BERT can process multiple input sentences with segment embeddings, we use the candidate long form as the first input segment. For example, Bayesian network. which is the long form of BNN, is placed at the beginning, and the given context as the second input segment. We separate these two input segments with the special token CLS and SEP. Furthermore, we add two special tokens start and end to wrap the acronym in the text, which enables that the acronym can get enough attention from the model. We use BERT as the encoder to get the representations of input segments. Since BERT may tokenize this acronym into several tokens, we average the representations of the start and the end positions of the acronym, and concatenate it with the CLS position vector. Then we send this concatenated vector into a binary classifier for prediction. The binary classifier including two dense layers using ReLU and sigmoid as the activate functions. Then we can obtain the probability that this expansion as the correct one. We predict the probability for each long form of one acronym one by one, and choose the long form with the highest prediction value as the correct one. Then we adopt the BCE loss to train the model. Besides, we also use several training strategies to further improve the performance. First, we test different pre-trained models to find the best one, mainly about two types, BERT and Roberta. Second, we utilized the dynamic negative sample selection strategy. We select a fixed number of negative samples for each bench to ensure the model is trained on a more balanced data. Third, we adopt the task-adaptive pre-training, which is abbreviated as TAPT, to pre-train the mask language model task on a given dataset. Fourth, we incorporate adversarial training by adding perturbations to the embedding layer to get more stable word representations and a more generalized model. Finally, we use pseudo-labeling. It is to use the trained model to predict the unlabeled dataset and add the pseudo-labels with high confidence into the training dataset to generate a new dataset. In order to choose the best pre-trained model for this task, we test different models including BERT-based, BERT-large, Roberta-based, CS Roberta, and SCI BERT. As the results shown, SCI BERT performs best, and maybe because our corpus are most of our corpus are from English papers. So we choose it as our base model, and the whole training procedure is shown in the screen. We use SCI dataset, SCI AD dataset to do TAPT on SCI BERT to generate a new pre-trained language model. Then we adopt dynamic negative sampling and adversarial training strategies during the training procedure to get the binary classification model. After this, we use pseudo-labeling to predict the unlabeled dataset and then train the final model. We do experiments on development set to verify the effectiveness of each training strategies, and the results show that all the strategy can improve the performance, and dynamic sampling is the most effective one. We also do the error analysis by gathering a sample of 100 development set examples that our model misclassified and look at these examples manually. From these examples, we find that there are two main cases where the model gives the wrong prediction. The first one is that the candidate expansions are too similar, even have the same meanings, just in different forms. For example, in the sentence, the SC is decreasing for increasing values of. The correct expansion for SC here is some capacities, while our prediction is some capacity, which has the same meaning with the correct one but in the singular form. The second one is that there is too little contextual information in the given context for prediction. For instance, the correct expansion for ML in sentence. ML models are usually much more complex. It's model logic. The predict expansion is machine learning. It is difficult for people because even people can hardly tell which one is right only based on the given sentence. Finally, we compare our results on the test data with other methods, and the results show the validity of our method, and we win the first place of SDU share task. That's all. Thanks a lot. Hi everyone.
Okay, thank you so much for your attention. And again, if you have any questions regarding this work, please reach out to the others. I think now we can move on to the last presentations of this workshop. It will be just a closing remark to summarize this workshop and also the ideas that we have to explore for the future work. Okay, thank you so much for attending this workshop and also for the great presentations. In this brief closing remark, I will just present some statistics of the workshop and talk about the main findings and the directions that we expect to see in the future. And if you have any other questions regarding the other issues about the workshop, please feel free to ask me at the end of the presentation. So in this workshop, we had 23 accepted papers. Here are the list of the main topics that we received submissions. Information extraction was the most popular one with 7 submissions. Tasks such as code reference resolutions, identity recognition, relation extraction are included in this group. We also had 5 submissions for information, veracity, and significance to assess the importance of the ideas, how influential they are, their reproducibility, or their augmenting the data set and knowledge base about the ideas mentioned in the papers. We received also 4 papers on biomedical text processing to analyze the uh, uh, biomedical text using the natural language processing techniques. We had 3 papers for scientific image processing to augment the data or to extract the textual part of the data images or to regender the generate the images in the scientific paper. We had two papers for the document classifications, for instance, to classify the domain of the document. And finally, two papers for the summarizations and reading comprehension. So in total, we had 14 long papers and 9 short papers in this workshop. The most of revisit keywords in the accepted papers is scientific and extracting knowledge, and also some keywords for graph representations, and some keywords for the biomedical text processing. In this workshop, we had some findings, and here are just a few of them that we can mention. We had some new tasks and resources for assessing the influence of the scientific papers in the literature, or to verify their information. We explored the existing transformer-based language models for different tasks in scientific document understanding. In this workshop, some new resources have been proposed for word embedding in this domain, some tools for library automations, and also some new resources for scientific image augmentations. And the papers presented in this workshop showed significant improvement in various tasks, including named entity recognitions, acronym identification and disambiguation, text summarizations, and reading comprehension, to name a few. And for the future, we expect to see more explainable AI for scientific domain, scientific document understanding. We expect that having more insights about the reasoning behind the predictions made by these models is important. So in the future, more explainable AI is required for this domain. Also, using the existing pre-trained language models for scientific document understanding is another direction to see more research on that. We know that there are a lot of pre-trained language models, and they have been also used in most of the papers presented in this workshop. But we know that all of these pre-trained language models are trained on different corpora and with different objectives. So having some methods to unify them could be another direction to explore in the future. And also more fact verification methods, especially by using external knowledge bases, or to populate the existing knowledge bases with this information, is also another direction that we explore to see in the future. And another direction that we expect to see is the transferring the knowledge between the sub communities. We know that there are a lot of parallel research, for instance, in the audio processing and in the natural language processing. And having some methods to transfer the knowledge between these communities and to unify their findings is another direction that we expect to see in the future. And at the end, I want to thank you for attending this workshop, and also for the great presentations that we had. We will reach out to you with more details about the proceedings and also the recording of this workshop. And again, I want to encourage you to join us to our poster session, which will be held in virtual chair in room E from 4:30 to 5:30. And we will present some works for the two shared tasks that we organized. So thank you again for attending, and I hope that you found this workshop helpful for your future research, and hopefully we will see more research on scientific document understanding in future. So if you have any questions, feel free to ask me, or you can email me after the workshop. Okay, thank you. So it will be the end of the presentation. So we will contact you with more details for the proceedings and the present recordings. Thanks.